Yeah, let's get started. Hi, everyone. Welcome to, this is CSE, 620, 2220, or CS 4220, Introduction to HPC. And this is the first lecture, yeah. So happy fall and thank you for coming. I implemented this last semester and I think it worked pretty well. So please put away your smartphones and your laptops. Oh, actually, okay. Did you see? Oh, are you able to see? Yeah.
For the future, our iPad. Okay, thank you.
The reason for this is the reason I don't want laptops. I use iPad charging because like if other people can't see it, one of the reasons for this is like I often find like if people in front are using laptops and they're doing something else, it's kind of distracting for people in the back. So I want it down. Maybe that's better. Paper and pencil is best, but if necessary, iPad is okay. And the reason for this is that, like I said, they're distracting, and especially if they're connected to the internet, usually folks are doing something else. If you have a special case, like somebody had, please let me know, and we can work something out. And my reasoning for this is that if you really want to use a laptop during the lectures are all recorded, so you are welcome to just watch them after and use your device during that time. Like I said, I'm going to post all the slides and the lecture videos. So the main thing that I want to do in this class is that I want everybody to feel free to ask any questions and answer my questions. So I will ask you a lot of questions. And the goal is that we can discuss the course materials, and hopefully that will help people understand it. And if anything's unclear, please let me know and we'll speak up. If you have comments or questions or anything like that. So the first half of this talk is going to be like syllabus, and the second half is going to be more about an introduction to HPC. So why should we take this? Almost all modern computers today are parallel, so we have to write algorithms and code to run efficiently on parallel machines. And parallel machines just means that if you have a problem, you can break it down into subproblems and do those parts at the same time for more efficiency. And basically, the only reason we care about parallelism is for speeding up problems, obviously. If you don't really care about speed, you can just run your program on a serial computer and you should be good. And another reason is that performance engineers, which are people that can improve the performance for programs, are in demand and will be necessary as problem and data sizes continue to grow. So I really think that parallel computing will be more important going forward, and I'll try to convince you in the next hour or so why. This one is actually a bit old, but I think the data is still relevant. So these plots are plots of like job listings. And this is just a measurement of how many are mentioning these words: performance, optimization, parallel, and concurrency, which is like a form of parallel computing. You can see that x-axis is time, and the y-axis is percentage. You can see that the percentage is increasing with time, and this data stops mostly like 2013 or so, but I would argue, though I don't have the data, that it is continuing to grow. The main objectives in the course, at the end, this course is mostly theoretical, but there is a practical component to it. For a more practical, like a very practical course, I will probably teach 60-30 in the fall, or in the spring, sorry. And so that will be like, if you're more interested in implementation and actual performance engineering stuff, you can take that. The main focus of this course is to design and analyze parallel algorithms and to learn parallel primitives and build advanced parallel algorithms from those, and implement those parallel programs using MPI, which is a high-level construct for a distributed memory program. Things that we are going to cover, like I said, this is mostly theory, but there will be some implementation assignments, memory hierarchy and analysis models, parallel algorithm analysis, which is the main focus of this class. So notions of measurement for parallel algorithms and notions of asymptotic analysis, primitives, prefix sums, it's like maybe one of the original parallel algorithms, and many others like communication primitives, matrix algorithms, so on. Models like communication networks, general techniques like load balancing, and like I said, parallel programming using MPI. So writing and executing MPI programs, collective communication, which are related communication primitives, and topologies, which are like what is the network topology that you're running on. What are we not going to do? Introductory algorithms and data structures. If you have not taken an introductory algorithms course, I suggest that you read CLRS or you try to concurrently take one because it is going to be super helpful. If you need a review, like in Big O, you can also CLRS. I've posted the entire PDF on Canvas. Check that. I also posted this asymptotic cheat sheet, which should remind you of some common Big O notations. We're not going to cover concurrency, which is a subfield of parallel algorithms, because that's like a whole other thing. And I did cover a little bit of it last semester, and there are other courses that cover it. So if you're interested in concurrency, you can take it next semester, or you can talk about it offline. And what I mean by like advanced practical performance engineering is very low level stuff like vectorization or like matrix or stuff like that. So we're not going to cover that. This is more like a high level algorithms overview. Like I said, you're going to need like undergrad algorithms or data structures, and ideally you can do C or C++, because MPI is built on C++. There will be a review on Friday. The TAs are going to run a review at 1 p.m. online on how to use the cluster. So all the assignments will be run using the PACE cluster. And this may be different from computing environments that you've used in the past. So usually, like when you have code, you just run it directly on your machine. And in the cluster, there's a separate machine, and you submit jobs to the separate machine, and they come back. So you have to remember not to run the programs directly on your own machine. You have to submit them to the cluster. So the TA review will cover how to do that process, and it will do some basic sequence as well. You don't need an expert. I'm going to post everything on Canvas. And time requirements, it's really hard to say, depends on your background. People do say that they spend a lot of time in this course because there's kind of a lot going on. There's theory, but there's also programming assignments. I try not to make it too much, but people also say that they get a lot out of it. So I will try to make it in line with previous semesters at least. Basic logistics, everything's going to be on Canvas. There's a discussion. We are working on, there's two sections, the 16-20 and 42-20. And the grading is separate. Just going to be separate classes, but pretty much all the material is going to be the same, and some exam problems might be different. We're working on trying to merge. I don't know if this is possible, but I want to merge the discussion boards because I think there'll be a lot of common questions. Not sure if it's possible, but I will get back to you. Academic honesty. Here's a link. I will talk more about it. Yeah. So what is plagiarism? Some examples. Listening while somebody else tells you the solution directly, basing your solution on an existing written solution, or copying your code or sharing your code directly with other students. And collaboration is something different. You can ask questions on the discussion board or to other students or to me or the TAs. Working together to find a good approach to solve a problem. You can discuss solution strategy at a high level, but try not to directly share the answer line by line. And if you collaborate with other students, please just write their names on your problem sets. You can discuss the assignments and collaborate with the other students. For the written homeworks, there's going to be like two parts of homework. One is like problem sets, and one is coding. For the problem sets, please write every solution on your own. And if you collaborate with other folks, just write their names on your solution as well. And don't refer to other assignments from the previous terms. Just go copy code, like more than a line, yes. And if you read someone else's code, try not to like read someone else's entire program. Just go off and base your solution on that. Yeah. So now we all know that we have ChatGPT. ChatGPT is actually not super good at HPC, so you might want to be careful. But in case, we will treat AI-based assistants like ChatGPT the same way we treat collaboration with other people. So you can ask questions for ChatGPT, but try not to like directly copy from the AI assistant, and don't like have them at the same time and like just write it on one window while you have it on the other. Basically the same document. Yeah, I think trivial things, I guess, in like MPI and stuff, but anything more complicated, you might want to verify the correctness. Okay, so I am Helen Shu. This is my email, and I will have office hours on Zoom at 11:12 on Tuesdays. My office is in Coda, but I know not everyone can get in, so I'm going to do this online. And the course link is actually here, so you can stand up.
Jake, I'll be the for the course 6220 and 4220. And yeah, we're looking forward to meet you all in your office hours. Also, like, please do not hesitate to put up your questions in the discussion board. Yeah, we try to answer all your questions.
Hey everyone, I'm Atharva. I will be your TA for 6220 and 4220, and we'll have a call on Monday and Thursday. If you have any queries, you can you can just put it on it. Thank you.
Yeah, and both Abhishek and Darwin took this class last semester. Yeah, so they know the material well, and they should be able to help you. And yeah, everybody's office hours at the same time at 11 to 12. And their office hours may be in person. I'm working on getting like we have a room in class that we can reserve. So when it comes out, I will reserve it. Questions? Yeah, so like I said, there's two main kinds of homework. Okay, so the first one is just this academic integrity homework. It's not meant to be hard. It's already on Canvas. It's just like a couple of questions, just making sure that you understand what this is. It's only 1 point. So it should mostly just be an exercise in LaTeX, which is like the typesetting software. There's two kinds of homework, like I said, written homeworks, which are problem sets. There are going to be 7 of them, and they are worth 2 points each. There will be about 5 problems per homework. This one you can work on with other folks. You just write the name. Programming assignments, there will be the first one. You can work on these in groups up to 3. The first one will be worth 3 points, and the remaining 2 will be worth 6 points. And for these, you just make one assignment, one submission per group, and we'll do the group assignments. Do that. There'll be 3 exams, 2 midterms. I'll tell you the dates in a second, and 1 final. This actually will take 20.
It was 2020 and 38.
Yeah. I think, yeah, reassign this later. We kind of put in 30. It's on the syllabus, right? Okay. In terms of deadlines for the problem sets and the programming assignments, they do it basically at midnight of the day. So like at the end of the day. So for example, if the deadline is this Wednesday, it would be like Wednesday at the end of the day. And for every assignment besides the exams, you have a free 48 hours. So if, for example, the assignment is due on a Wednesday, you can submit it up to Friday with no penalty. And that's just reflected in Canvas. Like there is a late assignment date in Canvas, but there will be no penalty applied. So you don't have to like post some kind of section or anything about it. Yeah. After the 48 hours, the assignment will not be accepted unless there's an emergency. So if there's an emergency, please let us know. You can make a private post in the discussion board. For grading, it follows the regular scheme. A is 90 to 100, B is 80 to 90, C is 70 to 80, D is 60 to 70, and F is anything below that. For pass-fail, please do all of the assignments and take the exams and get at least 50%. Yeah, so in terms of grading stuff, yes, one high level thing is, I think it's important to do hard problems because I think they help us learn. So the problems sometimes on the homework and exams may be challenging, but there will be a curve at the end to accommodate, depending on how hard they actually will be. And this is new, I think. I'm going to try to implement this and see how this goes. If you leave a question blank in an exam or a homework, written homework, not the programming assignment, you don't get any points if you leave the programming assignment. But if you leave any written homework or exam question blank, you can get 25% credit on that question. Not on the entire assignment, just on that single question. If you plagiarize or if you write something completely nonsense, you may get less than 25%. So the reason for this is to encourage you not to cheat, and also like if you really don't have time or like just don't write something that doesn't make any sense because it would waste graders' time and your own time to focus on that. So yeah, but you cannot pass if you read every single assignment. You only get 25%. Okay. Like I said, there's 7 problem sets and 1 academic integrity homework. The integrity homework is just to practice the typesetting. You can do the written homework in groups, just like your teammates, and please use LaTeX. Everybody will use LaTeX to make it standard. If you're unfamiliar with this, let us know. There's an example template on Canvas. There's a lot of online tutorials about how to do this. Yes. For the programming assignments, they're all on PACE ICE, which is this instructional cluster environment. It's a distributed cluster. There's several regular nodes on it, and there are outline instructions for logging in and using the cluster. Like I said, the TAs will also hold a review session on Friday to go through the commands that you need to run it. In total, there are going to be 3 programming assignments, all at NPI. You can do the assignments in groups up to 3, and everything will be submitted on Canvas or Gradescope. Last semester, Gradescope worked mostly better, so we're going to try to do all the submissions on Gradescope. There are 3 exams, 2 midterms and 1 final. The first midterm is on September 23rd. A little bit more than 1 month away. Second midterm is about a month after that, October 30th, and the final is December 6th, according to the matrix that they assigned us. If you cannot take a midterm exam at the scheduled time, so if you have a valid reason like conference travel or emergency, please let us know as soon as possible, at least 3 weeks before the midterm date, so we can make other arrangements, and we may have to schedule you earlier than the initially scheduled time, depending on the conflict. So if you already know this, let us know. Obviously, if you have a last-minute emergency, you cannot know 3 weeks before, but just let us know as soon as possible, and we can try to accommodate. And for every exam, you can get 1 just regular sheet, like back and forth to write whatever you need to write, like formulas or reminders or anything like that. Yeah. For accommodations, this is the Office of Disability Services, and please reach out to me directly if you have any special needs. For COVID and health accommodations, if you have healthcare issues, please just post the discussion privately, and we will work around whatever nearby deadlines there are. Okay, again, this is the last one. You have to do all your assignments and exams, your own writing and code, besides the group assignments, which are obviously in your group. Please don't copy the source code from other groups or the internet. Plagiarism will not be tolerated. I will go directly to OSI. So this is not to like be antagonistic, but just please don't do it. I don't want to deal with it. Questions?
The class size increase beyond current class size.
I will try to increase it. We're capped by the size of this room. Not have more people. I think the size of this room is a little more than 50. I don't know. I'll try to increase it at most of the classrooms.
So, does the class offer any extracurricular opportunities for projects, maybe exams?
Not currently. I think that's in line with previous semesters. You can correct me if I'm wrong.
There was only, I guess, only in one of the programming assignments they had an extra credit option.
Okay. There might be an extra credit option in one of the programming assignments, but there will be a curve at the end.
So for the programming assignments, it's groups of 3. Am I restricted just my section, or can I work with like people in other sections?
Oh yes, please work. Yes, indeed. For my the question was, can you work with people in other sections? Please try to work with people in your section because it makes the grading easier. It's hard to on Canvas do this grading in across sections. I will also make a post on the ed discussions for people to search for teammates. And it doesn't have to be exactly 3, because I don't know if the class size is the multiple of 3 or the section size, so it can be up to 3.
Is the coding applied to each assignment or to the overall grade?
The overall grade at the end.
Are you able to learn about GPU-based programming?
No, but if you take my class next semester, you will learn that. We can do. So I made like a course schedule, but the course schedule is subject to change. If there's a lot of interest, I think we have. I can't change the assignments right now to include CUDA, but I can maybe replace one of the assignments with like GPU model programming or like data parallelism if that's interesting. Yeah. Oh, also, yeah, thank you. I forgot to mention, I made this lecture schedule. I mean, I'm not going to pull it up now, but you can look at it. It's linked on Canvas. It's like every lecture, what are we going to do? And sorry. Yeah, it's a schedule of every lecture and what we're going to do, but we can obviously, like, if some lectures run long, I'm going to try to finish them in the next lecture, so that will be subject to change. But it will follow vaguely the schedule. And because that's mostly for exam purposes, like to know what topics will be on the exams, and I will tell you what topics will be in the exam. Probably like up to 1 week before will not be on the exam. That's too short to include it, but like everything before 1 week before the exam is there. So we can move on. That was the syllabus part. We're going to do introduction to HPC. Yeah, so the goal of the class, obviously, is to learn parallel computing. And the reason that we want to learn parallel computing, like I said, is to take advantage of modern hardware. Every big machine now is parallel. And like we mentioned, like there's a lot of interest in alternative, like traditionally it was in clusters. There's a lot of interest in alternative parallel machines now, like GPUs and even more specialized machines. So we're going to, but even if we don't do directly like computer programming, I think a lot of the models and the theory will be applicable. Like it will teach you how to break down the problem in a parallel way. So I hope that it should still be somewhat relevant. Yeah, why are we interested in this? To solve big problems. So like these are classical kind of applications, n-body simulation, molecular dynamics, multi-scale modeling. Obviously nowadays training LLMs is a huge problem that people are interested in doing in parallel. Big problems, and also you want to solve big problems faster because as problems grow, like doing regular methods, it's not possible to eventually finish the problem. You need parallel computing to even have a hope of solving it in reasonable time. So one metric that you want to improve in parallel computing is time. So you want to improve the quality of your answer or do as well as you can in your algorithm given the limits of communications or like the limits, depending on the size of the problem or difficulty of the problem, like limits is even like time that you have on this earth. Climate predictions, for example, one application that can take like infinite time, but you eventually want to, you can, one metric that people do is like they try to improve the fidelity of the simulation with some different metric. Another one that you want to improve another metric that you might want to improve is space. So you want to solve memory intensive problems. And one way that people solve the space problem is that you just add more machines and then you get more memory because you have more machines, but there's no limit how much that can save you depending on how fast the space is growing. So you might also want to apply special methods like compression to reduce the space. Yeah, so data analytics, networks, astrophysics, biology, these are all large problems. They have large data sets, like terabytes or even more. For the initial data set, not even talking about the actual problem that you're trying to solve, which may use more space than the input data. Usually use more space than the input data. Yes.
Does HPC always imply parallelism?
Not necessarily. Actually, so the first couple lectures are on parallel methods, but one area that I actually work a lot in is called like cache-friendly algorithms, which doesn't necessarily need parallelism. Like they go together. Like eventually you need both, but in terms of theoretical models and analysis, you don't actually need to involve parallelism in those initially. Good question.
Does HPC just involve distributing the load across CPUs or distributing those across multiple ones?
Good question. So HPC is a very broad topic. It can just even involve one node. Like we have multiple cores and multiple threads in one node. You can scale up to multiple nodes, both CPUs, GPUs, or like is it? HPC is maybe not super well defined. But I would say that multi-core programming is really interesting. We're not going to cover it though in this class. That's like OpenMP, but I'll do it this semester. So what is a parallel computer? The most basic kind of parallel computer nowadays is called shared memory multiprocessing, and it connects multiprocessors using a single memory system. So we can put that cartoon of what it looks like. You have one shared memory, and you have a bunch of processors, and they're connected to each other by the network. So your laptop is probably like this. Pretty much all regular CPUs are now like this. And this is an example of a chip. You have a bunch of cores. This is I/O. I/O takes a lot of space actually. The memory controller takes a lot of space, and then you have some shared L3. And elsewhere you may have a shared DRAM. And scaling out from that, each one of those machines in distributed memory processors is like one of this. So each one has a separate memory and it has a processor, which may also have multiple processors inside it. But usually from distributed memory, you kind of run the thing on its serial, at least at first. And distributed memory just means that every processor has its own separate memory, and then you need to do communication to pass things around. You can't all access the same data. And these often are also called clusters. So the base cluster is like this. You have multiple machines, and when you submit your job, it automatically assigns your job to some number of these machines, depending on what you specified in your command. And HPC system contains maybe 400 or 1,000 of this kind of node. So each of these is like, 64, 24 cores, whatever it is. Yeah, the base one is not huge. It's reasonably maybe on the order of tens of these nodes, but there's also not a ton of people using it. Like I said, pretty much every computer is parallel nowadays, but especially for scientific applications, this is one area that people are building these giant machines. So there's this list called the top 500, which is the fastest supercomputers in the world, the top 500 of them. And currently the largest supercomputer on the top 500 is called Frontier, which is at Oak Ridge, Michigan National Lab. Apart from here, actually, I think it's in Tennessee. It has 8.7 billion cores and runs almost 73 kilowatts. And this is the first exascale computer, which means that it can do over a quintillion calculations per second. So these are huge distributed machines, and there's people are interested in building them. They have large amounts. Yeah, so exascale has some clear definition. The basic unit of HPC is called a flop, which is a floating point operation. So that's like a multiplication, usually double precision, unless otherwise noted. And the main metric, so you measure operations in flops, and flops is floating point operations per second. And yeah, so that's speed or operations, and then the other dimension is size, which is measured in bytes. Bytes are just 8 bits. A double precision floating point number is 8 bytes. So that's 4 bits. And yeah, they're just prefixed with the regular units. So kiloflops is 1,000 flops per second. Gigaflops is 10 to the 9 flops per second. And then, like I said, right here is the first exascale computer. So exa is well defined at 10 to the 18 flops per second. And then you can also use the same thing to measure size. Kilobyte, you're probably familiar with these, kilobyte, gigabyte, terabyte, and so on. So this is the list of the top 500 from last November, but they redo this twice per year. And at that time, Frontier was number 1. And like I said, it has 8.7 million cores. And yeah, this is interesting. The second one is Aurora at Argonne. And yeah, actually, the third one's at Microsoft. Yeah, and you can see that these are all large, like on the order of millions of cores. And they have these measures, which I will tell you what they are. And they're measured on this Rmax and Rpeak. So I will just tell you what that means. The main measure that people use to measure the top 500 is called Rmax, which is the flops per second of performing this LinPack benchmark, which is basically dense linear algebra. We can think of LinPack kind of as like, yeah, it's dense linear algebra, it's bottlenecked by memory, hopefully it has a lot of flops to do. And yeah, this is a measure of the flops that you can do on LinPack, and this is the number one on the top 500, and this is number 500 on the top 500. And the green, I guess, is not that. Oh, the green is the sum of all the flops. Yeah, LinPack is solving this dense system of equations, AX equals B. And AX, or A is dense and it has random entries. So it's not a very complicated benchmark, but it's what it is. And it's dense, it's dominated by this dense benchmark. Actually, I want to go back to this one. Because I didn't mention RP is, so Rmax is how fast you actually got doing this benchmark, and RP is like how fast you can get analytically, which is you have some number of cores, and each core has a clock rate, and you just multiply them. So that's like the vendor optimal in some sense of how fast you can get. But obviously, RP is going to be higher than Rmax. Okay. All right, let's keep going then. So traditionally, one of the main drivers of HPC was scientific applications, like the national labs are maybe one of the people that are most interested in HPC to do scientific simulations and stuff like that. Yeah, so they've been doing simulations for a long time. They did it as the third pillar of science. Originally, in traditional science, we have theory and experimentation. Simulation is this third one that HPC can give us. And the reason that we're interested in doing high performance simulation is because a lot of things are inconvenient to measure with theory or experiment. Or to measure with experiment, I guess theory you can always do. But so like they're too big or too small, they might be too fast or too slow, they're expensive, they're dangerous. A lot of things are like this actually. Yeah, so even if you can do experiment, maybe it's also useful to do simulation. But especially a lot of phenomena are hard to do experimentation. So for example, last year at SC, the main prize winner was this giant climate simulation on Frontier. Yeah, on Frontier. Yeah, and they were doing this cloud simulation, and obviously this is energy intensive, compute intensive, because you have a lot of moving parts, and they were able to do, I think, the largest cloud simulation to date using this Frontier supercomputer. Another cool thing that they did, they did the same people, was they were doing like this molecular simulation for COVID, and they screened a bunch of compounds, and this is like in material science, like they wanted to identify which compounds are most promising for their particular. I think they're trying to do like drug discovery. So instead of doing experimentation on all these compounds and having to generate them, they can do simulation first, and then they can identify it. They can cut out a whole bunch of ones, but they don't need to actually create, because they're not going to be like as suitable for what they're trying to do. And there's a lot of things that people run on stuff like Frontier. Here are a few, like I mentioned climate a little bit. There's astrophysics, chemistry, genomics, earthquake simulation, cosmology. So these are all like basic science, but they are interested in doing simulation. In addition to simulation, another thing that people are interested in doing through HPC is data analysis. So once you do your simulation, or even once you do your experimentation, you may generate a lot of data. And if you do data analysis to try to process these things, again, things that are too big, complicated. If your thing is too fast, like you have stuff streaming in, like for example, you have an instrument and you take readings every 3 seconds, you need to do some kind of data reduction or analysis to understand what you're getting. Yeah, so even once you have done your measurement, even if you're actually doing an experiment, you still need to do some processing. Unfortunately, there's like, this is, I guess, reality in computing nowadays, which is, so this is one example, which is, like genomics. So you have a detector and a sequencer. The detector is the thing reading in the genome. The sequencer is the thing like processing it in a way that we can understand. And yeah, the y-axis is the rate of data growth relative to the starting point, which is at 1. And green is the processor speeds. So how fast is the clock rate in our machine increasing over time? And blue is memory speed, which is how fast can we transfer data from memory to processor over time. And you can see the detector is faster than the sequencer. So we are generating data faster than we can process it into human readable form. And the processor speed, which is how many cycles do we have to process this data, is also slower than the growth of data. And the memory speed, which is how fast can we bring in the data to be processed. So like you need to bring in the data before you process it here. And this is even slower than the rate of cycle growth. Yeah, this is called processor memory gap, and this is just like how hardware works. This gap is why we are interested in data movement, or yeah, in distributed memory it's called communication, which is like you pass the data around in your different nodes. In a stable machine, it's called like the cache behavior or like that. It could also be called communication. It's called data movement. And one thing that I work on, that I think is kind of cool, is like trying to optimize data movement. So you want to make this is your hardware limitation. So in software or in algorithms, you want to optimize for this. Either you can like reduce the data that you move, or you can be smarter about what data you move, or yeah, you rearrange your algorithm to move certain parts of the data first to make it more efficient. And I will tell you exactly what that means later. Yeah, so this is some more examples. For genomics, you have a bunch of these questions like microbes after wildfire, and these are data set types. 1.5 terabytes, 3 terabytes for carbon recycling, 4 terabytes for these microbes for disease and growth. Yeah, see, the point is that these data sets are large, like under terabytes, and you want to run algorithms which probably are even larger than the input size. Yeah, so nowadays everybody is interested in doing machine learning, which is another way that HPC has become relevant again. One way that machine learning makes HPC relevant is because it requires a lot of computing power to do. So this y-axis is the petaflops per day that you need to do training for ML models. The x-axis is time, and these are popular models like AlexNet, about nowadays going to AlphaGo. Yes.
When making HPC like these, is it common to like iteratively develop them or just like fully remake one?
When you say HPC systems, do you mean like the code or do you mean the computers? Oh, I'm trying to build them all at once, but it's a long time for the giant. But you can also build them later. Keep adding nodes. Yes.
In the previous slide, you mentioned that ML wasn't a fifth pillar. So is it a bucket that you're considering under data analysis or training models on this data?
I think I just put this here because it's more recent, and so I mean these are not like scientific classifications or anything. It's like ways to think about things. I guess you can think of machine learning as like it's in the same way that simulation is, like something that HPC supports that can also support science or other applications. Like there's no like usually like people do like machine learning for something, machine learning for drug discovery or whatever it is, and then you need cycles to support those models. So in the same way, I see like data analysis, you need HPC to do data analysis to support whatever it is. So in the back here, you can see that the petaflops per day that you need is increasing really fast. There's 300,000 times increase from 2011, which is AlexNet, to 2018 to AlphaGo 0, and we are even going past that. 2018 was a long time ago, and a lot has happened since then. So you can imagine that the situation is even worse worse than some centers from our perspective because you need cycles to support the training. And for reference, in a similar time frame from 2011 to 2017, the fastest top 500 machine grew less than 10x in terms of our max or our peak probably goes faster and our max goes lower. So obviously there's a mismatch between what we need and the top 500. You might argue like, well, their GPUs and also companies are usually training these things, so maybe the top companies machines are growing even faster than 10, but they're really not growing 300 times, 300,000 times. So usually they're probably like scaling out with like more GPUs, bigger clusters. This is just the same point basically that these machine learning models, you have to do more computing power. So the y-axis is the number of slots that you need to train these things. The x-axis is time. It's actually kind of interesting. So I guess they separated ML into like these three eras: deep learning, and then large scale. You can see that this huge like elbow when you come to start the deep learning time. I guess these are models. So like I said, usually these machine learning models, they take this huge amount of computing power to run, and they are for something. So for example, like AlphaFold is a celebrated advancement that they did in machine learning that they're doing protein structure prediction. And traditionally people do this experimentally, which is time consuming and it's hard, and like for it's probably NP-hard. AI can predict the protein shape at scale and accurately. So this was some really exciting like initial success, or not even initial success, like recent success of ML for scientific applications. Even more recent than that, I think I saw at Google, they did like AI for material discovery. So they discovered 2.2 million new crystals, which is a huge scientific advancement equivalent to 800 years of knowledge. And so this is the graph that they showed in their article. For human experimentation, they got 20,000. Maybe this is interesting crystals because for this thing, they labeled 421,000. And for experimentation, they got 20,000. Yeah, and from traditional computational methods, they got 42,000. So that's like non-machine learning methods, just simulation or traditional HPC. Okay.
Yeah, could you go back to the previous slide? So I'm assuming when we use like just a other people kind of use like linear experimenting with our computation methods, it is some sort of a move forward where we are trying to explore every possibility that we know, right? So then and then we're talking about like a neural network that explores like orders of magnitude more possibilities in a way. Like so my question is how does the AI is able to do that, and does that also just consume way more resources and like time? Because you mentioned on the slide before that it's time consuming and challenging to do brute force, but then AI is predicting more possibilities. So isn't it also time consuming in a way, making more resources?
Yes, I mean you can see like this number of flops
Yeah.
that is needed for AI. Like in terms of like the advancements they're making, it's not free. Like you need this many cycles. I think maybe nobody, or at least I don't understand well like why AI works. Or, like I think a lot of people don't understand this, like how, like I think like reproducibility or like understandability is a huge field right now in AI. Somebody who knows more about AI can tell me more. But like trying to understand like exactly why these advancements are happening, or like under what conditions are they happening, is very open, and people are interested in working on that. People who know more about AI than I do. Why do I think like that? I mean, I think like I don't think like from human experimentation and computational methods, like there's probably some what am I trying to say? Like they're probably not exploring every single option. Like there's probably some people who know about this area, for example, like material discovery, they probably can eliminate, like do some kind of like elimination of, obviously this is not going to work, but I think AI is just like, I don't know, it has like more data, so it's able to understand like, it's able to understand or predict like things that direct discovery is not able to. Sorry, to answer your question.
Yeah, so there are more optimization side.
Sorry?
Like, I feel like with the human experimentation or competition methods, we are more to make some sort of a optimization, maybe in a greedy manner, which reduces some of the possibilities.
I think maybe there's also like some limitation, like the number of possibilities that humans can explore is less than the number of possibilities that like huge, gigantic CPU clusters can explore. So yeah, also that. Interesting.
Computational method has like limitations. In material science, basically like you have different computation, like different models for different type of like for the like whatever you want to simulate, let's say. So you'll have certain model for a particular type of simulation, and like that just restricts you from experiment. So for different materials, you'll have to just go and develop more models. And also, like these methods, like they sometimes uh, like the calculations that they just go to zero. Like sometimes there are many challenges that depending on what the conditions and like whatever the conditions that you set, like specifically for uh, materials and the temperature and all those things. Like it's just like depends on the model. So it's very open ended. Yeah.
Thank you. Good. Okay. Cool. Thank you.
I was wondering if I don't know, we see the questions before, but also some power. You know, like different variables a lot of people don't have limited power. What do you expect to work to?
Yeah, it's a really good question. I think like they are, I guess like given the machines that we have, like time, like reducing the time can in some cases reduce the power to run machines for less time. I guess that's one way from like the algorithm side that it reduces the power. Another way is like memory movement is related to power, so if you reduce the memory movement can also help you just like reduce the number of cycles that you need to run. There's like specific work, I guess, like low power computing is like changing the actual hardware, or yeah, you can also like I guess do some kind of hardware thing where you like you adaptively change the power that you need with your algorithm. I don't actually know a lot about that, but it would be interesting. I think power is not one of like the theoretical measures that we're using in class, but it is for sure like an interesting like empirical, more on the empirical side of things. Yeah, let me get back to you. I can change my electricity power. Thank you. Okay, so why are all computers parallel? Yeah, I guess there's three main trends about why computers are parallel nowadays. One is like we need parallelism for performance, and I will explain like it's not optimizing for power, but power is one of the reasons for it. There's data locality, which is related to memory movement, and there's hardware specialization related to physical limitations. The y-axis is relative growth, and so on. The x-axis is time, and the gray is transistor count. The blue is clock speeds. And I don't know, maybe you've already heard this before. Until 2004, there's Moore's law, which is the scaling of clock frequency about 2x every 2 years, which is like this. And sometimes like we have these pre-performance gains from a software perspective, not from a hardware perspective. But with the underlying hardware changes, if like during this era, if you had your code and you waited 2 years and you bought another machine, your algorithm would be twice as fast with no changes to your actual code, which is great. That's called Moore's law. This is due to like semiconductor miniaturization, increasing the clock speeds of our machines. So for example, these are Apple computers with similar prices over time. So this is an Apple II from 1977. The clock rate was 1 megahertz. The memory is 48 kilobytes, and it was about $1,400. In 2000, the clock rate goes to 400 megahertz, and the memory is now 64 megabytes, and the cost is still 300. And here in 2004, the clock rate is now 1.8 gigahertz, and the memory is 356 megabytes, and the cost is 1,500. You can see, like, controlling for price-ish, the clock rate and the data size are increasing. So your machine has access to more your machine has access to more resources, and then your algorithm can do bigger and also faster with no real change. This is like a traditional figure for this thing. The amount of power, or the power density that you need to support these increases in speed. X-axis again is time, y-axis is power density, which is watts per centimeter squared. And around 2000, like, the reason that we care about this power density is because it's cooling to deal with this. And as you can see, like, if we were to continue on the trajectory that we were around 2004, it would become difficult because this is way too practical in any reasonable way if you just do this on one chip. So, yeah. One question that this gives us is there's two ways to improve, like, your speed in your machine. One is that you can improve the frequency or the number of cycles you can do per second. Another one is that you can improve the cores, which is the number of processors that you have on your single chip. Turns out that the performance is basically like the cores times frequency from an analytical perspective, and the power is related to cores times frequency to the 2.5. Yeah, so originally people were increasing the frequency. That was like from semiconductors by increasing like the density of the semiconductors, and then once the frequency became too high from this perspective, they started increasing the cores. And that is how they got the initial parallel computers, which are the multi-cores. So like around 2004, they started getting popular. This is an example from 2011. There's 8 cores. There's 8 cores. It has this 3.3 gigahertz, and it has 15 megabytes of free cache. So like I said, they share a number of machines. You have these multiple cores, and then they share this cache. And then you need to deal with the cache management. That's a separate issue. And yeah, to scale the performance, once we ran out of like the ability, like from a power perspective, once we ran out of this ability to increase the number of semiconductors, we started just copying the processors that they had and putting them on one chip. And each generation of Moore's law potentially doubles the number of cores. Like I said, cycles per core times number of cores. You can either increase the cycles or the cores. So if you want to keep doubling, you gotta increase the cores. And this is, yeah, so I said we ran into this wall around 2004, and then the transistors kind of flattened out. The processors, yeah, this clock speed also kind of flattened out, so the clock speed per core is not really improving, but the number of cores is, the green is number of cores, is 1 for a long time until 2004, and then it is growing from there. Which is kind of interesting because like parallel computing is older than 2004. I think the parallel algorithms before that in the 70s. But they just didn't have parallel computers back then. So I guess they were thinking. Another thing is where are these performance gains coming from? One is the multi-cores, like I said, this reddish color. This thing only starts in like 2004 or so. But before that, all the benefits are coming from frequency scaling or pipelining, which is like not a software thing or an algorithm thing. So yeah, pipelining starting from around here, and for a long time that is like all there is. There's frequency scaling is this huge fraction of the improvement. Pipelining gets you some, and then starting here you get superscalar execution, which is again not necessarily a multi-core thing, but that doesn't get you a lot. Like here it's pretty small, and here it's still not a huge share of performance. Starting from 2006-ish, I think that's correct. Well, you get multi-cores, which gives you a bunch, and blue is SIMD, which is a kind of parallelism in a sense, and dark blue very recently is used multiply add in the parallelism.
Is power a limiting factor? So I saw a couple of slides ago, it said that it's like cores times frequency. So is there like between cores and frequency, is there one which had improved more
courses?
Nowadays people are mostly improving course because power like needs grows more with frequency than the course. But for a while, like until they ran into these physical limitations, it would be their only increase in the frequency. And SIMD is just one kind of parallelism. Just one of the lectures to be all about SIMD or data parallel processing, which is just in your machine, it turns out that you have these things called SIMD units. Like traditionally, you do like, for example, you have two operands and you do some operation, and you get some answer, who's like A plus B, for example. But actually, often, like rather than A plus B, you would like A of 0, A of 1, A of 2, so like an array. Plus, you want to like add two arrays, for example. So you can do a bunch of them in parallel in a specific hardware unit. So like rather than your people familiar with registers. Okay. So rather than like normally registers hold one thing, now you have vector registers which hold like 4 or 8 things. So you just apply the same operation on the entire vector register and you can do a bunch of them in parallel. But this is not like it's not like multi-threading or it's not a multi-core. Like you can do this on one thread. Yeah, but it's a kind of parallelism. It's called data parallelism. And most processors, you have SIMD units with 2 to 8 way parallelism. And actually, like maybe you can argue that GPUs are very highly based on SIMD parallelism. Yeah, GPUs use SIMD parallelism as their main parallel. Let's see paradigm. Yeah. So parallelism is everywhere. This is like a phone chip in CPUs and GPUs. You can scale up. These are like not huge cores, but yeah, these are phone chips. It's like 8 cores, 48 cores, and there's also like all the way on the other side. There's this huge distributed machines like right here. Yeah. So the entire point of this is that no matter what scale you're on, like your phone or your supercomputer, you need to care about parallelism. This is like the most original rule in parallel computing, which is called Engel's law. And Engel's law tells us that how much speed up we can possibly expect from a parallel program. Which how you value actual speed up that you can get. So suppose you have an application and part of it is parallel. And Engel's law tells us that you have 2 parts of your program. One is the fraction of work done serially, which is S, and then 1 minus S, which is the parallelizable fraction. And if you have 2 processors, it's like I don't know, a very simple thing, where the speed up is bounded above. Parallel processing can only help you in the parallelizable fraction. Because like the serializable fraction is just fixed. So your speed up is bounded above by 1 over S, where S is like the fraction of your program that is serial. Yeah. So this is saying that even if you perfectly speed up your parallel section, performance is limited by how much of your thing is sequential. So this is an example, like if your parallel portion is 95%, you can improve almost with P. If it's 75%, even 90%, you can only get this bounded speed up. So, and even before that, like 75% here, 50% is here. So this is just telling you that you want to make as much of your program parallel as possible. Because even a little serial portion can get your speed up.
So whenever we say power, it's the power which is required to run the system, right? So if you want to increase the frequency, the required power to run that system is going to increase, right?
Yes.
But if you want to, if you increase the number of cores, that means more transistors are included into the system or the processor. That means heat dissipation is more. So we need more power for cooling as well, right?
Yes.
So do we most likely not consider that because most of the processors might not run beyond 90 or 90, the general desktop.
Can you say it again?
When we say
Do you
power,
not consider the power when you run?
to cool down the systems
Yes.
because of the increased heat dissipation.
Yes. From a theoretical standpoint, we don't measure the power at all, which is maybe problematic. And it would be interesting to come up with theoretical. I think maybe one is that like I think there are some theoretical works that try to consider like the relationship between power and the number of cycles that you run. But normally, like even in serial programming, you're only counting like the operations or the instructions. You're not really counting how much power it is per instruction. So I think most traditional parallel models are also based on the serial models, which are only counting like instructions or operations but it does, yes, it doesn't matter how much power you use for sure. Yeah, so this can somebody asked about, is HPC just parallelism? I would argue that it's not, especially, I guess to me, like there's two major aspects to HPC. One is parallelism and the other one is data locality. And the reason that you care about data locality is because, like I said, the speed of data movement goes even slower than the clock speed. And so often you are not bottlenecked by your clock speed, you're bottlenecked by like how fast you're just moving data through your system. And yeah, so there's two main metrics. And I guess this is related to power. Like one is speed. I guess the relationship between power and speed is like the faster your program runs, the faster you can shut it off. And if your system can do this optimization, then you can like shut off the entire system when you're done, or you can, if some cores are not in use, you can shut off those particular cores. But not all machines can use such fine-grained assets, so this is like the active area of work. Yeah. So first motivating trait for these machines is parallelism. Another one is data locality. Like I said, data locality is important because memory is scarce and it grows way slower than processor speed. So there's this 2000x gap between processor speed and memory speed. Yeah, y-axis is performance relative to the starting point, and x-axis is time. And the reason for this is hardware physical limitations. And so the memory wall, or this gap between memory latency and the latency of floating point operations, which is your processor speed, this gap is increasing exponentially over time. So even if your processor, in some sense, like even if you increase your processor speed infinitely fast, like you're still bottlenecked by how fast you're just engaging with the processors, which is why like often increasing the parallelism may not, if your thing is memory bottleneck, increasing the parallelism may not have you in many cases. Yeah, so parallelization alone is not enough because of this gap between the two. This is just some benchmark for memory movement. So this red line is transistor's growth over time, and this blue line is the stream benchmark, which is a very simple benchmark for memory bandwidth. If we're just going to sum or something, if you just sum numbers in an array. And then y-axis is relative scaling over time. So again, this time, and this is growing much slower. It doubles maybe like every 2.9 years. This is Moore's law, which is every 2-ish years. Yeah, this is a philosophical question, like where data is involved, is compute scaling irrelevant? For example, like I said, like even if it's like 5x per year for your users, if your memory is still bottlenecked here, does it matter so much? Maybe. I don't know. You can tell me later after the course. Yeah, and the last one that I want to talk about really briefly is specialization, which is not going to be covered in detail, but I just want to talk about it briefly because nowadays you can't really talk about HPC without specialization. So specialization, by specialization I mean like hardware specialization, building specific chips for tasks. And this is a lot of data, you don't have to look at it all, but basically the point is that like in general processors, there's a lot of stuff going on. Like for example, like you have your basic instruction set, we also have other stuff like in the very long instruction word, operation queues, stuff like that. You have a lot of, because it's a general processor, like you need stuff to support general programs. However, if you can build a specialized chip like a basic, you can get rid of a lot of the unnecessary hardware, like a lot of the unnecessary operations and stuff like that. And so this bar is for energy consumption. So it's saying like how much energy consumption is coming from supporting these different types of functionality. And this generalized with specialization, you can increase the energy consumption significantly by getting rid of this stuff that you don't. And this is like the opposite side, this is speed up. And it's saying like this like line is the ASIC, and this original line is just basic risk. And the speed up for your ASIC is higher because again, like you don't need to deal with control flow as much for like the other stuff. However, like on the other side, obviously, then you pay generality for getting this improved energy. Oh yeah, okay, so this is just saying like you can improve both energy and time with hardware specialization. And many argue that specialization is endgame for Moore's law, in the sense that like energy efficiency, like operations per joule, is most efficient with special purpose hardware. Because of course, like you can get rid of all the stuff that you don't need, and you just keep what you do. And to get maximum energy efficiency, you should just focus on everything six. Yeah, so then, so I have like 2 more slides. I hope that I have convinced you that traditional scaling has come to an end, and this is why we care about doing parallel computing. In the beginning, we had these basic instruction sets like RISC. The multi-core era was like 2004 to 2010. This is the end of Java scaling. We got multi-core like during Moore's law, we had 2x every 1.5 years or so. In multi-core, we got 2x every 3.5 years. And now even that is kind of falling off. 2010, we're doing 2x every 6 years. And now 2x every 20 years or something like that. And so the real paper, maybe you should read it. I can upload it. There's plenty of room up top. And it talks about like in this era of the end of hardware scaling in some sense, like what should we be doing? Or in the end of general hardware scaling, what should we be? So they talk about 3 directions. One is software, one is algorithms, and the last one is hardware architecture. So by hardware it means like specialized processors, like instead of specialization, or yeah. So simplifying processors and also domain specialization, like building specialized ASICs for your application. The ones that we will talk about are software, which is software performance engineering, and that is reducing like software overheads and also optimizing your software to hardware features. Maybe you can do that. Yeah, you can argue that like MPI or parallelism is in this category, and then algorithms is like on the more theoretical side, coming up with new algorithms, new models to target specific architectures and new problem domains. And in this class, we are in the first mostly in algorithms. I don't know, we're not doing new algorithms. I would say that they're really good. But next semester and last semester, we thought more about performance engineering.